Chris Richardson, please take it away and educate us on all things good about microservices and where DDD fits and where it's insufficient.
Yes. Yeah, it's actually quite interesting. When I wrote, Indu asked me for a title a couple of months ago, and I quickly threw something together. And then about 2 weeks ago, when I sat down and started writing the talk, I feel like it might have diverged slightly from the original title, because a lot of the emphasis is really on the whole concept of designing software systems that are loosely coupled and highly cohesive. I sort of talk about that a lot and how that's actually necessary but insufficient, but I do touch on DDD as well. Let's get this thing right. So yeah, so let's imagine that you, for whatever reason, have decided, hopefully a good reason, which I'm going to talk about shortly as well, have decided to use the microservice architecture. So, you know, the essence of using microservices isn't going and like setting up Kubernetes and splitting an application just into Docker containers blindly, even though there's a lot of sort of focus on the technology side. It turns out that what really matters is defining your services, identifying them, defining their responsibilities, their APIs, their collaborations. And that's really critical to get right. And the technical part of it is primarily, I don't want to be too dismissive, but it's kind of read the manual stuff. Like you read the Kubernetes manual and the Prometheus manual, and it's actually hard because a lot of modern technology is a pain in the butt to use, but it is more read the manual kind of stuff rather than just sort of architecture and software design principles. So that's kind of a key point, is that defining your services is the essential challenge. And, you know, it makes sense actually to use DDD. Adrian Cockcroft a million years ago made a very explicit connection between microservices and DDD, where you know, if you actually dig into it, I'm not really sure what with bounded context actually means, but it sort of implies maybe that a service is a bounded context. And so it's like simply use DDD to identify your bounded context and then just translate them into services, and you could be done. Turns out, of course, there's a bit more to it than that. But to kind of echo a point that we were discussing prior to the start of the talk, I think you actually need to, an organization needs to have really good design skills. In particular, I think an organization has to have good knowledge of DDD in order to succeed with the microservice architecture, because it is all about getting your service boundaries correct. And sadly, and sort of in my experience, a lot of organizations kind of struggle with actual solid design. So there most definitely is a place for DDD. And then if you take a step back and just look at sort of more timeless concepts within the software engineering community, you know, I think, you know, which is really all about good naming, right, which plays a pretty central role in DDD as well, but also the concepts of designing software elements to be loosely coupled and highly cohesive. I mean, who can really argue with that, right? But once again, this turns out to be all sort of good stuff that you need to take into account. But what I'm going to show in this talk is that there's actually a set of more physically oriented design principles, which is sort of around like teams and collaboration and productivity, and then really techie stuff like the fact that services are communicating over a network which have latency and finite bandwidth. And then you also have to deal with practical things like transaction management and consistency and isolation. which are not traditionally sort of considered when you're sort of doing software design, at least in the object-oriented design DDD sense of the word. Yeah, there's a little bit about how aggregates are consistency boundaries, but I'd argue that's a little different than the full concept of a database transaction. And as sort of the background suggests, there's got a space metaphor here. I use the concepts of dark energy and dark matter from astrophysics as as metaphors for the microservice architecture design principles. So that's the topic, but before we talk about that, I just want to briefly introduce myself. So obviously I'm Chris. Been building software for a million years. Back in the late 80s, I worked on Lisp systems. Later I got into Java. I wrote the book POJOs in Action, which was all about Spring and Hibernate. Back in 2008, in the early days of cloud computing, I created Cloud Foundry, which was a PaaS that ran on top of EC2. So that was 2008. That eventually got acquired by SpringSource and then VMware. And that's where the name Pivotal Cloud Foundry comes from, or whatever it's called today. Tanzu, something or other, perhaps. So I've been doing a bunch of stuff. And then really for the past 12 years, I sort of stumbled across this wild and crazy idea of not building a monolith and functionally decomposing your system into separate deployable pieces. And I started sort of working in that field in sort of 2012. And that eventually became known as the microservice architecture. So that's kind of what I've been doing for rather a long time now. And so, I help organizations around the world through consulting and training use the microservice architecture successfully. So that's me. So here's the agenda. Going to talk about just sort of logical design principles with a focus on coupling and cohesion, briefly introduce the microservice architecture, and then talk about these sort of mysterious dark energy, dark matter forces, which respectively encourage decomposition, push you in the direction of using finer grained services, and then also dark matter forces, which actually resist decomposition and push you in the direction of using a monolith. And they're actually in conflict. And sort of your job as an architect is to find the appropriate trade, sort of balance of these conflicting forces. So that's the talk. Let's just dig in. So, software design is sort of a somewhat broad field, right? But I think the most important part of it, in a sense, beyond actually producing working software, is naming and organizing software elements. I mean, that's what it is at its core, right? So, classes, packages, and then subdomains, right? To use a sort of DDD term. And a big part of it is actually organizing elements into a software hierarchy to make change easy. Working software is obviously necessary, but it's insufficient. We need software that's easy to change as well. So you could sort of view that as grouping methods and fields to form classes, grouping classes to form packages, and grouping packages to form subdomains or bounded contexts, or whatever word you like to use. With the goal of making it easy to change. So a pretty ancient idea in the software community dating back 50 plus years is the idea that software is easy to change if the elements that comprise that software are loosely coupled and highly cohesive. Parnas wrote this very famous paper back in 1972, which was basically about modularity and encapsulation with the goal of achieving loose coupling. And then another influential book, 78, about structured design, basically sort of said similar things. So that's why the talk is really focused on sort of loose coupling, high cohesion, and contrasting those principles with these more physical design principles I'll talk about later. So let's look at loose coupling. So specifically, this is design time coupling, because as I'm also going to talk about later, there's actually another form of coupling that is a little different. So design time coupling, or the degree of design time coupling between two software elements, between two classes, say, is the likelihood of needing to change both of them for the same reason. And then if these elements are tightly coupled, that means that they frequently change together for the same reason. So you can actually see this physically, like if you look at a GitHub repo or a collection of repos, imagine there's a Jira issue, and then you see commits that are affecting multiple software elements or multiple commits in multiple service repositories, all related back to the same Jira issue. That's evidence of tight coupling or of coupling. And if you see that frequently, that's evidence of tight coupling. And this is bad in general, because tight coupling increases the scope of a change. Instead of changing one element, you have to change at least two elements. There's more to understand, more to change. And then it's really bad if those elements are owned by different teams, because if you apply Conway's law, in order to have loosely coupled teams, they need to own loosely coupled software components. And so if those components are tightly coupled, then those teams are having to coordinate and communicate far too much, right? Which I think is a symptom in a lot of organizations where people seem to spend forever in meetings, aligning, coordinating, communicating. I remember prior to COVID, visiting clients, and it was hard to find meeting rooms. And I'd argue that's because these organizations were just too tightly coupled, constantly having to communicate, coordinate work. And therefore, minimizing coupling is really important. But what's interesting about, and there's a few principles that you can apply, right? And this is all in the realm of encapsulation and information hiding. And one metaphor that I particularly like to use is to think of a software element as an iceberg. It has a small, stable API, that's the visible part of the element, that encapsulates a much larger implementation, which since it's hidden, hopefully by the API, can be changed much more freely. And then there's some other principles like, Uncle Bob has a dependency inversion principle, which says, an element should depend upon interfaces and not on a concrete sort of implementation of an element. And then there's also the interface segregation principle, which kind of encourages you to define sort of now, instead of a single broad interface for a software element, actually define multiple narrow interfaces. So a change to one of those will only impact the clients that use that interface and not other clients that don't. So anyway, so that's designing for loose coupling. The other principle, which I've always sort of struggled with in a kind of weird way, is this notion of cohesion, where the idea is that you design elements, composite elements like a package, which is the collection of classes, to be cohesive, which means that they consist of tightly coupled sub-elements. And when I've been reading about this for years, and it was like, well, why would you design elements to be tightly coupled? But this is actually recognizing the fact that coupling is unavoidable. There will be elements that are coupled in your system. And the idea is you put them in one place. So if you have a bunch of classes that are coupled, you act like, in this case, A, B, and C, you put them together in the same package in order to localize the change, right? So if they were scattered across multiple packages, because they were tightly coupled, you when you make a change, have to go look at all these different packages. Whereas if you design the package to be cohesive, those coupled classes are in one place. And then the other aspect of cohesion is classes that are not tightly coupled goes somewhere else. So in this example, D, which is not coupled to A, B, and C, goes in its own package. And it's kind of an interesting idea. It sort of minimizes the size of these composite elements like packages. Then you're wondering, we got a whole bunch of classes that don't seem to be coupled to one another. Does that mean we have a whole lot of little packages? And it's like, I was thinking maybe, or you just have a util package, which is a big bucket that you put everything in. That's just kind of a common thing, right? Where it's like, if you don't know where to put stuff, you put it in a util package. And there's various principles that can boost cohesion, like the common closure principle, which actually is basically all about cohesion. Things that change together should be packaged together. And then the separation of concerns principle, which just sort of pushes things apart that are somewhat unrelated. Anyway, so we've got loose coupling, designing for loose coupling, designing for high cohesion. And that's sort of a big part of what software design is all about. Oh yeah, I think I already talked about that. And interestingly, you could sort of view coupling as this attractive force between elements where it encourages you to put them together in the same place. Whereas the other aspect of cohesion acts as a repulsive force, which encourages you to put things in different places if they are not tightly coupled. And I'm going to come back to this metaphor when I talk about dark energy forces, which are actually repulsive forces, which encourage you to put elements in separate services, versus dark matter forces, which are attractive forces, which encourage you to put them in one place. And interestingly, coupling is actually an attractive force in the microservice architecture. And these concepts of coupling and cohesion appear in a few places in DDD book, turns out. Like the concept of a module or a package in DDD is actually, it talks about having loosely coupled, highly cohesive packages. And then one of the really interesting patterns, segregated core, is all about sort of distilling the core domain down so that it's somewhat minimal, highly cohesive, and loosely coupled to the rest of the code. And I think that's like this concept of the segregated core is kind of a really powerful concept. So anyway, so that's sort of loose coupling and cohesion. So then sort of where do microservices fit in? Well, you might just view them as another level in this hierarchy, right? So instead of having a single monolithic application comprised of subdomains, which are comprised of packages, you actually have this extra level where the application is comprised of services. And it's like, well, okay, maybe they're just another element, and the whole principle of coupling and cohesion apply to those as well. And what I'm going to show is that it's sort of, yes, coupling and cohesion are useful, but there are some other concerns as well, these sort of physical principles. Was there a comment? Okay. Yeah. So, okay, then let's look at what microservices are all about. So I want to just talk about like why microservices. And the argument sort of goes like this: sort of the modern world is actually, well, it's kind of crazy, but more sort of formal way of saying it is sort of volatile, uncertain, complex, ambiguous, right? Where from businesses face new competitors like bricks and mortar bank, face online banks, then then there's COVID comes along, and that actually had a big impact on IT. Like online shopping just jumped ahead 5 years. Online grocery shopping jumped ahead 5 years, I think I read. Though it's kind of gone back to normal, I think. And, businesses have to thrive in this crazy world. And given that businesses are powered by software, that means that IT needs to deliver software much more rapidly, frequently, reliably, and sustainably than before, right, in order for businesses to compete. And you can actually quantify that by the DORA metrics. So these are the DevOps metrics. But in order to accomplish rapid, frequent, reliable software delivery, you need what I call the success triangle, which is basically embracing DevOps as defined by the DevOps handbook, which is continuous delivery.
Sorry, let me try to mute. Sorry, I'm trying to mute folks. I think folks joined.
No worries.
For people in the call, could you please mute yourself? I'm unable to mute some folks. Okay. Mute all. There we go. But okay.
Chris, you muted yourself too.
You muted me. Okay.
I'll unmute you, but yes.
All right. I think you can hear me now. So yeah, you need the success triangle in order to deliver software rapidly, frequently, reliably. In other words, you need three things. You need process, namely DevOps, right, which is as defined by the DevOps handbook, which embraces continuous delivery and deployment principles. You need to structure the organization as a network of small, loosely coupled product teams, in other words, do what team topology says. Instead of product teams, they call them stream-aligned teams, right? So we've got these small teams practicing DevOps principles, and then you need an architecture to support that, which turns out needs to be loosely coupled. Surprise, surprise, right? Because you need a loosely coupled architecture to enable the teams to be loosely coupled. But then in order to support continuous delivery and deployment, it needs to be testable and deployable as well. And sometimes you can achieve that with the monolithic architecture, but for a large application developed by a lot of people, the monolithic architecture can just have too much friction, which then has encouraged people to use the microservice architecture. So the big idea behind the microservice architecture is that it structures the application as a collection of loosely coupled, coupling again, independently deployable services. So executable, deployable units, whatever that means in the technology that you're using. And independently deployable means that you can actually build, test a service and then be independently of any other service and actually be confident that it's ready, that is production ready, and you should just deploy it into production. And I'm going to come back to the precise definition of loosely coupled as well. And they tend to be organized around business capabilities, which is like, gosh, that sounds like subdomains or bounded context from DDD. And they're typically owned by a small team. And it's actually all to enable teams to work independently. So yeah, if you look at this individual service, it has a name, it has a set of responsibilities, it has an API operations that can be invoked synchronously or asynchronously. Its API also can include events, and then it can collaborate with other services. So that's sort of one perspective on what a service is. Another perspective on what a service is that it's a bunch of code, application code, and then also infrastructure code such as Terraform or Kubernetes YAML that resides in a Git repository. Changes are, when you make a change, that triggers the deployment pipeline, which builds and tests and then deploys that service into production. And then in production, there's multiple instances running in production, along with its supporting infrastructure, like it will have its own private database server, for example, maybe a cache and other pieces of infrastructure. as well. There's obviously shared infrastructure like a message broker and so on. And then the other sort of part of this, which I kind of find interesting, is that you can view a service as a collection of what I call subdomains. You might want to call them bounded context, but each one is a slice of business functionality that is owned by a team. So in this example, I've got a service which actually consists of 3 bounded contexts, each one owned by a particular team. But it turns out that ideally, a service should probably have 1 subdomain, which is owned by 1 team. But for reasons I'll explain later, that might not be the case. So yeah, so, in other words, you could employ DDD, identify your subdomains, bounded context, map each one to a service, and maybe that would give you a good service architecture. And then similarly, you can apply design for loose coupling and high cohesion. And that probably gets you in the direction of a good architecture as well, right? You've got cohesive services that consist of just exclusively of subdomains that are tightly coupled. And given that you want your services to be loosely coupled, from that perspective, having cohesive services makes perfect sense, because it means that those services are sort of by definition loosely coupled. So that's it's kind of getting you in the right direction. But then it turns out that there's a whole set of other concerns. So you could sort of view it as somewhat insufficient. And this is where the metaphors of dark energy and dark matter come in. So dark energy is this sort of mysterious anti-gravity that's causing the expansion of the universe to accelerate. So somehow astrophysicists that look at distant galaxies and look at their velocity, and it appears that, was it 7 billion years ago, suddenly the universe, well, for the first 7 billion years, the expansion of the universe slowed down, as you would expect, but then it accelerated, which is like, what the heck? That makes no sense. So they invented this concept of dark energy as an anti-gravity to cause that. And that's a metaphor for the repulsive forces that encourage you to put subdomains inside different services. So you can think of it as pushing subdomains apart, just like dark energy is pushing the matter of the universe apart. Simple services and fast deployment pipeline and so on. And I'll talk about each one of those in a minute. But then conversely, you have these attractive forces that are resisting decomposition, encouraging you to use a monolith. And the metaphor for that is dark matter, which is another concept that astrophysicists invented to explain observations. And that's an invisible matter, which apparently comprises 85% of the universe that you cannot see, and you can only see indirectly through its gravitational effect on stars and galaxies. And that's the metaphor for the attractive forces that encourage you to put subdomains together. And interestingly, that's actually a lot to do with coupling between subdomains, where you want to put subdomains that are coupled together inside the same service. But there are other reasons, and a lot of that is to do with operations that span multiple subdomains. There's a lot of benefit to be gained if you make those operations local to one service by putting that operation's subdomains together within a single service. But sort of you ultimately go down that path, you end up with a monolith, right? If every operation is local. So here are the dark energy, dark matter forces. So there's five of each. And I'm going to explain each one of them in a little bit more detail later. But the idea that services should be simple, teams should be autonomous, deployment pipelines should be fast, the need for multiple technology stacks encourages you to separate subdomains, put them inside separate services. But then conversely, the need for simple, efficient interactions between services encourages you to put subdomains together. The need for ACID transactions instead of eventually consistent transactions encourages you to put them together as well. And then also to minimize coupling. But surprise, surprise, there's actually two different types of coupling we're talking about here. Design time coupling, which is what I talked about earlier, but also runtime coupling. So it's a little bit more complicated than just simply designing for high cohesion and loose design time coupling. There are all these sort of physical concerns to do with networks and databases and team productivity that you don't normally consider when doing sort of traditional object-oriented design or DDD. And then obviously the really interesting thing here is that these repulsive forces and attractive forces are actually in conflict with one another. The repulsive forces are encouraging you to have a fine-grained architecture. The attractive forces are encouraging you to have a monolith. And so your job as an architect is to sort of make the appropriate trade-offs and sort of decide when to violate or not resolve some of those forces in order to achieve a good architecture. Okay, so let's talk about dark energy forces. So these are the repulsive forces that encourage you to put subdomains in different services. And it's sort of somewhat related to cohesion. So if you think about cohesion, which is pulling tightly coupled subdomains together into a same service, but at the same time, it's saying those subdomains that are not tightly coupled go somewhere else. It's sort of pushing things apart at the same time, but it might push things apart in the same way as these forces, but it's not actually guaranteed to. So there's sort of a different kind of, there's sort of a conflict between the traditional kind of concept of cohesion and some of the goals that we need to achieve here. So the first force is simple services, which I also go by the name of components as well, right? Simple services. And that's sort of the idea that the more complex a service has, the more dependencies it has, and perhaps the more complex and diverse its runtime behavior is, the harder it is to sort of understand, develop, test, troubleshoot, and so on. So by putting subdomains in separate services, you just make things simpler. So that's sort of the first principle. So in theory, if you followed this, every subdomain should just be in its own service, which is interesting. The second principle is this notion of team autonomy. If two teams, imagine team A owns subdomain A, team B owns subdomain B, and they are packaged together inside the same service, they will need to those two teams will actually need to work together at some point and coordinate changes. It's like, even if it's something like a version upgrade of a dependent library, right? Team A might want that, but that creates work for team B, or vice versa. Or just the fact that someone on one team can check in code that breaks the build, and so there's a potential for interference, right? And that all impacts productivity. So there's great motivation for having one service per team, or at least, or a team could have multiple services, but a service is only ever owned and worked on by a single team. So once again, that's pushing subdomains that are owned by different teams into separate services. Now, one big kind of related point here is that subdomains that are owned by different teams need to be loosely coupled from a design time perspective in order to make those teams loosely coupled. So that sort of has big consequences for the relationship between teams and subdomains. It might even mean that if you have two subdomains that are tightly coupled for some reason, perhaps you should just have one big team, even though that might violate the team topology guidelines, because that still might be better than having two teams that are constantly having to meet. Another really critical thing is you need a fast deployment pipeline, right? Fast feedback from the tests in your deployment pipeline and from production is essential. And, you know, you can certainly apply technology to accelerate, to make your deployment pipeline go faster, but ultimately you actually need to reduce the size of what the deployment pipeline is building and testing, and then also actually have multiple deployment pipelines, right? And you know, with the model that each service can have its own deployment pipeline, which is building and testing services independently. So once again, that's sort of encouraging you to push put subdomains into their separate services in order to accelerate the build. Another really interesting consideration is the need for multiple technology stacks. So, you know, subdomains are packaged together inside the same service. They have to use the same technology stack, the same runtime implementation, the same sort of application framework. There's, like in Java, there's essentially a single class path, so they have to use the same version of all the dependencies and so on. And sometimes subdomains need to use different technology stacks, which then encourages you to put them inside different services. So you could have a Java service and a Python service, or a Spring Boot service, and for whatever reason, I don't know, a Quarkus service, that kind of thing. And then the other aspect, so that's sort of one aspect of technology stacks in your architecture. And then the other aspect is you need to keep your technology stack up to date, right? You know, new versions come out, vulnerabilities get fixed, and so on. And you have to keep your application's technology stack current. And that's a lot easier to do if you've got multiple services which can each be upgraded incrementally, one small upgrade task at a time, as opposed to having to upgrade an entire giant monolith. So that's also another aspect of sort of technology stacks that encourages you to put subdomains inside different services. And then the fifth and final force, which is sort of a bucket of related concerns, is so subdomains have characteristics and like resource requirements in terms of, I mean, which in like a crude sense is what kind of EC2 instance do they run on best, right? And also there's a regulatory aspect to it as well. And then there's also a business criticality, availability aspect, security aspect, and then also like DDD core versus non-core subdomains. And the idea here is that you want to segregate subdomains that have differing characteristics, because in each case you will actually have some benefit, like improving security or improving availability. So like one example of this is, let's imagine that you have a subdomain that uses an expensive resource like GPUs. Like I think on EC2 instances that have GPUs are like 8 times the cost of general purpose instances, right? And so if you have a subdomain that uses GPUs packaged with a subdomain that does not, but you need a lot of instances of that other subdomain, you actually have to scale subdomain B as well, and hence over provision your GPUs, which actually wastes a lot of money. So that's a good reason to actually put subdomains with differing resource requirements in separate services so that they can be scaled independently, which is much cheaper and, you know, minimizes waste and so on. So that's sort of one sort of characteristic based sort of separation of subdomains. Another one is segregating by business criticality. Remember years ago, I consulted with this company that processed credit cards, and they had a monolith. And the interesting thing about that, right, is they make their money from the APIs for charging credit cards, right? 3% plus whatever, 30 cents per transaction. So, and if that API is down, they are losing money, and they'll probably get sued by, by their major customers, right? And so there's a huge sort of benefit to be obtained by actually putting the business critical subdomains inside their own services and actually running them on separate infrastructure and making sure that they are very loosely coupled from a runtime perspective with from the rest of the system, which, while it's important, is far less critical. No one is going to sue you if your merchant management UI is down, whereas if your payment processing API is down, you're in serious trouble. But so segregating by business criticality is really important. And then, I've also talked with companies who are developing software in the medical realm. And this is a great example of a domain where software development is regulated. Yeah, you can't employ regular DevOps, and you have to develop according to these ISO standards. Don't know what they mean, but it sounds unpleasant, right? But if you think about a medical application, only say some parts of it are actually really governed by FDA, SAMD regulations, right? And the rest of the application is not. So by segregating it along the lines of these regulatory requirements, you can hopefully just a small part of your application needs to be developed in the slower way, whereas the rest of it can be on sort of the DevOps fast track. So that's another concern. Another reason to segregate. And as I said, there are multiple kind of characteristics that you can use to segregate your subdomains. So those are all wonderful reasons to put subdomains in different services. And some of them are aligned with cohesion, some of them are not. So I now want to look at the dark matter forces, which are the concerns or goals that actually resist decomposition. And they are mostly generated by the system operations that span multiple subdomains. And for the simple reason that your software is a lot simpler, or an operation is a lot simpler when it's local to a single service. And the more distributed it is, the more scattered its subdomains are across multiple services, the more, should we say, problematic it is. And then there's also the issue of design time coupling between subdomains, which encourages you to put them together as well. So anyway, so sort of, this sort of the notion of design time coupling as an attractive force that encourages you to co-locate coupled services is definitely aligned with regular software design principles. But then there's these other forces that actually, for sort of very physical reasons, you end up having to put subdomains together, which actually makes services less cohesive, because you're not just using design time coupling as the packaging criteria. But design time coupling is certainly a big goal, right? Like, a defining characteristic of the microservice architecture is that the services are loosely coupled, which means that they should rarely change in lockstep. And so if you have tightly coupled subdomains in different services, you're likely to be in a world of pain. And in the ultimate sort of case, you've built a distributed monolith where large number of services are changing in lockstep, and you basically have a monolith with all of the complexity of the microservice architecture. Because, for example, you're usually running in a zero downtime environment where you can't just shut down the world and then sort of atomically deploy multiple new versions of multiple services in one go. You have to do it in an incremental fashion, right? So let's imagine that the customer service API changed in a breaking way. Or you'd actually have to, for a while, the customer service would need to support the old and the new versions of that API. You then have to go and convince all of the client teams to migrate to that new version of the API. Hopefully they'll do that eventually, though they might hate you if that interferes with their priorities. And then only then can you remove the old version of the API. So these changes across service boundaries are actually quite expensive. So that's why having loosely coupled services from a design time perspective is really essential. And sort of the best way to do that is if you have subdomains that are tightly coupled, put them together inside the same service, right? So it's sort of following the cohesion principle there. Maybe you could get away with having tightly coupled services provided they're actually in the same code repository, because at least then a given change is limited to a single Git repository. But then you still have the issue of deployments of multiple services are not atomic, and then you've got API evolution issues and so on. So it's really best to package together tightly coupled subdomains. Okay, so that's I sort of talked about the last of these 5 forces first. Now, if I jump back to the beginning of the list, right? Another goal is you really want to have interactions simple. So if you have a system operation that's distributed, it could actually be difficult to understand. You imagine create order operation is failing, and well, it appears to fail in service A, but well, if service A is calling service B, well, you figure out that it's service B, but then, oh, when you look in B's log, it's actually because C is failing, and so on and so forth. So actually troubleshooting failures of a distributed operation can actually be quite time consuming. Even, just trying to figure out the root cause of the failure, and the longer it takes, the longer you're down and the less available your system is. So sort of this complex interactions between services for a given operation, is cognitively harder, it takes longer to troubleshoot, and it can reduce your availability. So there's a really good motivation for making an operation local to a single service. You just look in its log if there's a problem, right? And in some ways, it's sort of easier to understand as well. There's also an efficiency argument as well, right? Like the network has latency, it has limited bandwidth, right? This is always one of the unavoidable problems of distributed systems. Sometimes it doesn't matter, but sometimes if the pattern of communication between subdomains in order to implement a given operation involves lots and lots of network round trips or lots and lots of data, it might be too expensive to make it a distributed operation, and you need to, once again, co-locate these subdomains. Even if they're not tightly coupled from a design time perspective. So it's sort of an efficiency efficiency can force you to actually have services that are, but by definition, less cohesive. There's another similar argument to be made about transaction management as well. If you have an operation that's actually distributed, it ends up needing to be eventually consistent because transaction boundaries are generally limited to a single service, right? So and if it's distributed, that is multiple transactions, and you basically have eventual consistency. Specifically, you end up having to use, like, say, the Saga pattern, the CQRS pattern in some form, or the API composition pattern. So if you want an operation to be implemented using an ACID transaction, which is simpler, right, you actually have to co-locate its subdomains and make it local. So, you know, that's overriding any concept of cohesion as well. Yeah, because it's just so, I mean, it's like, it's very doable. I mean, eventual consistency obviously works using the Saga pattern and so on, but it's just more complicated. Oh, and then another really critical issue, this is another kind of coupling, right? In reality, there's actually multiple types of coupling. You know, until now, I've talked about design time coupling. There's also runtime coupling, and runtime, that's sort of the degree of runtime coupling between two services is the degree to which the availability of service A is impacted by the availability of service B. So here's one example of tight runtime coupling. So imagine, you know, a post request to create an order comes into the order service. It makes a put request to the customer service, waits for a response to come back, and then the order service can respond to its client. That can only work if both services are available simultaneously. So the availability of this create order endpoint is basically the product of the availability of those two services. In other words, it's less than the availability of an individual service. And you know, with working with clients, I've seen cases where you end up with like long chains involving up to like 10 services, which means you lose 1/9 of availability. There's one client I worked with where, you know, it's sort of like this, where there was order management, and they might have had a couple of services that didn't seem so bad. And I was talking with the order management team, and they go, oh yeah, we just call the fraud service. And then I talked with the fraud service, and it turned out that fraud management was like maybe 6 services. They were sort of following the one service per developer anti-pattern. And so it's sort of this interesting thing when you have sort of siloed teams, you don't necessarily know how many services are involved. And in this particular case, this company was integrating with an e-commerce vendor, and they had a pretty strict SLA, and which was a risk from these long chains of synchronous calls. So that's sort of the desire to minimize runtime coupling can actually encourages you to put service subdomains together within the same service, which once again, you know, results in less cohesive services. So that's another sort of example of sort of a physical principle of availability, which actually can influence your design. Anyway, so it's sort of like that's my talk, actually. So if I were to summarize, right, like sort of applying DDD concepts and identifying subdomains, that's really helpful when defining your architecture. And then, you know, following the concepts of loose coupling and high cohesion, especially loose coupling, right, because that's an essential part of the microservice architecture. You know, that's really important as well. But then on top of that, there's all these sort of more physically oriented kind of design goals or forces that you have to achieve, right? The dark energy, dark matter forces. And especially the whole dark matter forces, which mean that you just for reasons of efficiency or transaction management or to minimize or to reduce latency and maximize availability, you have to put subdomains together, even though they are not necessarily, even though they might not be tightly coupled from a design time perspective. So anyway, that's my talk. Hope you found it useful, and thank you for listening.
Hey, thank you, Chris. That was very, very knowledgeable and useful. And let me see there. Feel free to unmute yourself and ask Chris if you have any questions. I'm scanning the channel for questions. I know Christian had a question, I think, on the slide where you had the cohesion. Can you go back to that slide? I think he was asking.
What is that? Okay, whoops. Yeah, let me share my screen.
Sorry. Christian, are you still on the call?
Yes, I'm here.
Yeah. Do you want to ask your question?
Yeah, it just triggered me that I would probably think that cohesive mean that things are closely related, like three animals would be related, and maybe not a tool. But of course, if they're related, maybe they're also often very tightly coupled. So maybe that follows that if things are related, then they're also coupled. But I'm not native English speaking, so that would, I just thought a bit about that.
Yeah, it is interesting. It's I feel like there's sort of like some aspects of coupling, you know, I think there's a degree of overloading, right? And, you know, in a sense, I was looking at it from the narrow perspective of what makes software easy to change, right? Or from the goal of minimizing design time coupling. And yeah, there's the other argument of this sort of somewhat nebulous concept of functionally related.
Yeah.
Which might mean, and which you feel like, yeah, we want to put them together because they feel like they belong, right? And then it's like, well, does that truly help? And what does that mean does it help in terms of ease of change or not?
Yeah, so you say in reality, it's more about coupling than it's about relatedness, because maybe they looks related, but it doesn't give any effect if they're not closely coupled. Maybe that's what you mean.
Yeah.
Yeah. Good point.
Thank you, Chris. I think for me, like what really resonated was like when you're making the trade-off and you have to take the team's composition or your organization's, I guess, hierarchy or how the teams are organized into the architecture, because in order for the teams to be truly autonomous, it might make sense for them to own their own services, especially if they are the people that are working on the tech and so on. But then you said, in that case, it's better to have loosely coupled. So, so for me, it kind of like the loosely coupled is through messages and event-driven architecture, where where there isn't, like you also mentioned, where there was a chain of 6 services calling each other synchronously. So so with messaging, I feel like even with the team autonomy, you can get that loose coupling using messaging or asynchronous tech. I see the frown on that.
Yeah. Well, I think this is the problem. I actually think that there are actually 2 different types of coupling. So what you're talking about is loose runtime coupling, right? Which
oh yeah,
it's funny, this is sort of an abbreviated deck of, was it? So, like, if we go back to this example, one way to avoid or to sort of reduce runtime coupling is for the post operation to initiate a saga and return immediately. And then there's a bunch of messages that bounce around, right? Like credit is reserved in the customer service, inventory is reserved in the inventory service, right?
Right, because in this example, like order service is a different bounded context, right? So it's probably, and then customer care is probably a different bounded context.
Yes, exactly. I mean, yeah. I mean, in my terminology, which you can criticize me for, I would say that there is an order management subdomain which gets packaged. And you could call that just this whole DDD meaning of words thing is so ironic. But they're actually two entirely different forms of coupling. Right, so using messaging here, right, so the create order operation initiates saga, that improves the availability. It makes it more complex for the client because this order service is returning a partial outcome, and its client would have to check back later to find out whether the order was created successfully or not, right?
Yeah.
But the critical point is that this is different from design time coupling, right? Which is the likelihood of having to change together. So you could have an order service that is invoked asynchronously, but has an unstable messaging-based API, which constantly changes, which then requires the order service to change in lockstep. Right. And if they're owned by different teams, those teams are having to meet, align, coordinate, and all of that stuff. Right.
Yeah, definitely.
So if you want to have teams that work independently, that the software that they own has to be loosely coupled from a design time perspective.
Yeah, 100%. Yep.
Can I ask a thanks for the talk, by the way. It's very interesting, sort of bringing some kind of practical steps to the sort of abstract DDD, like we've got subdomains, we're all done, sort of concept. So my question is kind of, do you have any advice as far as within like a code base, maybe it's a larger code base, employing sort of strong design time decoupling within a code base to give the option of runtime decoupling later when it demands it? DevOps supports it. You're able to do distributed tracing and all that sort of stuff. There's service-oriented architecture and these sorts of things, but there's lots of different sort of extremes you could go to in that concept of like getting a code base saying, we don't know if it's going to split or maybe it'll never split or whatnot, but we need to kind of have these things separated. So there could be, and one extreme, something which is that, things just call whatever and the files or wherever they are and packages as they are. And then another extreme could be like a service calling its own APIs externally to say like, even though they're together, we're going to like pretend like it's at any point in time, these things can split up,
Yeah. I mean, this is sort of like the concept of the modular monolith, right? And I feel like there's degrees of modularity. I think the bare minimum is having a monolithic code base that isn't organized around technical layers like web domain persistence, right? Which is like the old way, but actually organize it around subdomains or whatever you want to call them, right? So the top level would be order management, customer management, so on and so forth. And then within that, you would have web domain persistence, and then inside order, inside each one. So I think having a sort of domain-oriented organization for a large code base is a good first step of achieving modularity. Now, then where it gets interesting is exactly how should you take it even in a more modular sense, right? Like, and there's sort of two aspects to that which come to mind, which are kind of related, is should subdomains communicate asynchronously, right? Because it's like if you were to put if you wanted to have the option of putting subdomains A and B in their own service, then actually there's two things. One is they might need to communicate asynchronously, right? And then also the transaction boundaries should perhaps be scoped to a single subdomain. And so, which then means within inside your monolith, you are actually using sagas and other eventual consistency mechanisms. And it's like, partially it's like, yeah, maybe, or maybe there are parts that you should do that. But the problem is, as soon as you start going down this route of having sort of a monolith that's got these characteristics of a distributed system, you're now incurring a lot of the cost and the complexity of the microservice architecture without actually having any of the benefits. So part of me just wants to yell, Yagni, right? You ain't going to need it. But then the other part of me goes, yeah, this notion of making sure that you are preserving the option of decoupling might be worthwhile. Could be a good thing. So it's possible that you want to do a cost benefit trade-off, right? And some parts of your monolith should be more loosely coupled than other parts. Perhaps.
Yeah, that makes sense.
Trade-off.
Oh, sorry.
No, go ahead. Yeah.
I was going to say, having been on the receiving end of combining microservices, it definitely is splitting them up now is a more thoughtful process. To what degree they actually need to, and what are the actual subdomains, and when do you know that okay, we actually have legitimate sort of technical need or Conway's law need to actually have these things separate versus this idea that like, well, wouldn't it be nice to just have these nano services and they do like two things and they all communicate and all that sort of stuff. But yeah. Thanks for the answer.
I mean, it's interesting. Oliver, I forget his last name, who works on one of the Spring guys. He's got this whole like Spring modulith project. If I got the name right. It's funny, I just read his tweets. I never actually have to say it out loud. Or rarely. So he's done some interesting stuff, and I feel like he's going in the direction of sort of this extreme modularity where there's loose sort of runtime coupling and limited transaction boundaries within the subdomains in the monolith. And it's, as I said, it's like, maybe.
Yeah.
We're coming up on time, but I have one question from Kuram. I hope I pronounced your name right.
Yes, it's good. Induis Horan. So, Chris, since you mentioned, team topologies and Conway's law, one of the things that I wanted to see how you handle where an organization wants to move from their monolith to microservices, but the team organization currently they have does not support it, right? So how do you go about, because that's a very tough nut to crack, how you break the news, how you handle that where the team organization has to change to support the modern architecture?
Yeah. Well, I really feel that it's sort of a necessity. I mean, like and I think this is true with adoption of a number of different technologies that like improve organizational agility, like cloud adoption, for example, right? Where you don't just adopt the technology, you have to change your process and organization as well, which is why I came up with this concept of the success triangle, right? Namely, you need the architecture, and you could substitute adopting the cloud as well, but you need the right process, and then you need the right organizational structure as well. And I think it's a common anti-pattern to do the technology or the sort of the architecture bit and ignore everything else. And I call that the red, if you go to microservices.io, it's one of the red flag law anti-pattern of adoption. Yeah, but that organizations just sort of, I mean, just need to do it, which I agree is hard. Right now we're in the category of sort of organizational change, and how do you make that happen? But number one is convincing people with the ability to change the organization that it needs to be done, right? I mean, I think that's number one. And then, yeah, it's like, you know, if you view migrating to microservices as this sort of iterative incremental migration where you're carving off chunks of the architecture, sort of one service at a time, you end up needing to incrementally change your organization as well. And then also for the services that are you know, for each service, the teams that work on them have to sort of follow DevOps principles as defined by the DevOps handbook. And so it's all to do with people, right? Which is terribly messy and difficult. But it's like if you don't, then you're now you could say this is like why adoption of agile in the enterprise is not entirely successful as well, right? Because it's like people, there is this organizational inertia,
right?
But you know, I guess it depends on how big a crisis it is, right? But you know, there's a good argument to be made is that if you know, in today's world, if a company wants to be successful, then it actually has to embrace all of this this approach to and deliver software rapidly, frequently, and reliably. Because unless it's got some kind of monopoly, then it will be outcompeted, right? Worst case, Apple or Amazon will start competing with you in the same business, right? Yeah.
And I think like in this case, it really helps to have an ally. Like when I say ally, like your manager or like the organizations like VP. And so I think the first job is to try to convince them to help them see the picture.
Oh yeah. Yeah. I mean, that's yeah, I should have pointed that out. It's like, yeah, I mean, it's, you know, sometimes the business is behind the push to do better because the as-is state is actually causing business problems, right? And in a way, that's a better situation to be in because, say, the business is losing money and the business wants to fix the problem, so they will come to the engineering group and go and say, what do you need to go faster, right? But then in the other case, which is perhaps the more common case, you as an engineer need to build a business case, right? Like, oh, if we extract this part of our monolith into a service, we can iterate, we can test it more thoroughly, which will reduce the number of bugs, which will make customers happy, less likely to abandon our product, fewer calls to the support center, which reduce costs. And then you just make up a dollar amount with this will be the cost saving or this will be increased revenue.
Right. You need to speak the language that the business understands to push that forward. So in that proposal, like, you know, make all those arguments that are important for them in that can help. But again, I think it requires a really strong ally.
Yeah. Yeah, and yeah, I mean, a business product manager once says you just have to make up numbers like the business does, and just be confident when you do it. But yeah, you need, I think ultimately you need a senior person who actually wants to do differently.
Yeah.
Well, one wants to do better, right? And I think it can be tough if you don't have that.
Yeah, thank you. You have definitely given me some ideas with the challenges I face in my organization, and I'll follow that up. Thank you.
Yeah.
Cool.
Yeah, by the way, I should say, please, feel free to reach out if you've got questions. Shoot me an email.
Thank you.
Awesome. There was one question in the chat about CQRS, but like I think 4 minutes is a very short time to tackle it, but I'll read out the question. How could CQRS be used in relation to a distributed business transaction? I understand how a Saga or a process manager could help, but I'm not sure I understand how CQRS could be useful. That is a very loaded question, and I'm not sure if
I will answer it really, really quickly. I speak fast. Well, so there's a couple of different uses for CQRS. So one sort of pure use of CQRS is when you have a query like find order history that needs to gather data from multiple services, right? You could implement it using API composition, query each one of those services individually, or you can apply the CQRS pattern and localize it, right? In one, have a replica in one service that you just query. So the find order history operation is now local to a single service. I mean, it's working off replicated data, so there's consistency issues. The other thing that's interesting is, so part of this is around efficiency. This is like resolving the efficiency force. It also minimizes runtime coupling as well. The other use of it is let's imagine you create an order. In order to create an order, you have to, for a food delivery service, you have to validate and price the menu items, right? So one option is the order service interacts with the restaurant service and sort of dynamically makes a request, right? Perhaps as part of a Saga. But an alternative way is for the restaurant service to basically, is to use a CQRS, and for the order service to maintain a replica of those parts of the restaurant's menu that it needs in order to validate and price an order. So it's sort of not this kind of, I'm leaning in the direction of calling this the command side replica pattern, because the motivation is not to implement a query, but to simplify the implementation of a command. And the value for that is that the create order operation can do more validation locally and return a more complete response to the client. In fact, like if the operation only spans 2 services, and by replicating data from one to the other, you've made that operation local in a sense, and you've improved its availability.
Sure, I fully understand that. I just didn't connect CQRS with having the local replica. I just thought CQRS more like the separation of the write and read side. But of course, if you subscribe to events from the other service, then you can localize the copy, and then you don't have to call them.
Yeah, I mean, in this context, it's possible that this is not pure CQRS in the strict meaning of the word, the original meaning of the word, right? It's more like use events to replicate data so it can be queried.
Yeah, sure. But I understand it now. Thanks.
Awesome. Thank you. Thank you so much.